So now we're going to start to look at the idea of induction. To get to it, we're going to start by introducing a concept that we're sort of familiar with, and that's the idea of flux. But this time not electric flux as we've seen before, but obviously magnetic flux. Now the basic definition is very, very similar to the electric flux, and so it won't take us very long to get started. And so we're going to use the symbol phi. Sometimes you'll see it like this, but with a B. Sometimes just the circle and line. They're the same thing, and they are the magnetic flux. And our easiest way to start to begin to describe it is to say that it is very similar to electric flux. And we've done a lot of work with electric flux. We derived electric flux. We used it to find a relationship between electric field and charge enclosed, eventually giving us Gauss's law. But it's going to help us with something very, very different when it comes to magnetism. And so do recall that our definition of flux, after quite a bit of deriving, going from the basic definition of electric field lines passing through some area, we were able to derive the general formula that the electric field dot product with this dA vector, where A is a surface, is going to give us the flux. And so that defines the electric field lines through some area A, giving us the flux. We're going to not reproduce that definition because it is identical for magnetic flux. But instead of electric field, of course, we will use magnetic field. And so we have B dot dA. And so that is our most basic definition. I wouldn't say basic, but certainly most general definition. Yes, general definition of the magnetic flux as well as the electric flux. Now we went on and showed what the electric flux was equal to. I believe it was Q enclosed divided by epsilon naught. We'll see that in a second. Here we're going to get something very different for magnetism. But before we do that, let me just give a little bit of a reminder of how you solve this B dot dA integral or E dot dA integral, either one. So just a little bit of a reminder. Let's say recall. If I have some surface, and I'll just define this as my surface, then a little piece of that surface located on the surface that is perpendicular to the surface is the definition of dA vector. And so the whole surface here is A, the area of the entire thing. We could define, again, we're looking at it edge on, pretend that's like a piece of paper or something like that, but you're looking at it edge on. It's not a line, it's a surface. If I turned it this way, it would look like a square. If I turn it this way, it looks kind of like a line. dA is a tiny little subsection, of infinitesimally little small piece of that overall area, and its direction is always going to be defined as perpendicular to our surface. Next thing we're going to do is we're going to add some magnetic field lines. Let's throw some magnetic field lines in this direction. And they go all the way through. I don't want to draw it, but they're going all the way through like so. And so this is our B. And if I was to try to calculate what the B dot dA is for that value, so just focusing on this part of my magnetic field equation, we take the magnitude as we always do. The magnitude of a dot product is just the magnitude of the first multiplied by the magnitude of the second multiplied by the angle between them. All right, so we have our B, we have our dA. What is our theta in this problem? What is the angle between B and dA here, right? Now you might look at it and say that the angle of the difference between B and A look like they're parallel to each other, but remember it's dA that is perpendicular to our area. And so the angle between those two lines is clearly 90 degrees. And so this becomes cosine of 90 degrees, which goes to 0, and the whole thing comes to 0. Basically, you get a magnetic flux equal to 0. Okay, and that totally makes sense. It's consistent with what we learned with our electric field as well. If I have some surface like this, and I have electric field lines that are going here and here, none of those electric field lines are passing through our surface. They're all running parallel to it, and so there will be no flux. Very different than what we see if we should, let's say, turn that paper or surface 90 degrees. Again, our edge on view, is going to look like this. There's our paper or surface edge on, and we'll have our dA vector be a tiny little piece of that area perpendicular to the surface. So there's dA. And our magnetic field, I'm just going to make it the same direction as before, is going like so. Okay, so now what's the angle going to be between our two values? Our B and our dA, clearly it's going to be 0, of course. And so let's see how that affects this example. And I'll start all the way with my B dot dA. The other one I didn't have to add the integral because I knew it was going to end up being 0, but you could have kept the integral there as well. Now we do the magnitude of what's inside the integral, and we have, oh, you know what, I shouldn't use the closed integral sign just yet. And so we'll have the integral B dot dA, I'll explain that in a second, is B times dA times the cosine of the angle between them, which you all told me is 0. Of course, cos of 0 goes to 1. B slips out of our integral, as we've done many times before, and we are left with B times A. So the flux through a surface, as we see over here, where B is going perpendicular, where basically B is constant and going perpendicular through our surface A, is just going to be B times A. It's exactly what it was for the electric field. No surprises so far at all. So if we are using our electric flux, we're going to need some units. So the SI units for, magnetic flux, well, let's see, if it's B, which is Tesla, and A, which is meter squared, I reckon is going to be 1 Tesla meter squared, like so, which has another name. It gets to be called 1 Weber. And that's the SI unit for the magnetic flux, 1 Weber. So now that we know that the magnetic flux is always going to be the integral of B dot dA, we also kind of want to know what the right-hand side is going to be equal to. Like, what would the equivalent be for Gauss's law versus the magnetic? Basically, is there a Gauss's law version of magnetism? Well, it's going to be very different for magnetism than it was for the electric field and the electric flux, because remember that electric charges can occur as monopoles. In fact, that's the default. We either have a positive charge or a negative charge. Unlike with magnetism, we found out that magnetics or magnets are naturally found as dipoles. That is, we expect to find a positive and a negative, a north and a south, with any given magnet that we have. And so if we are trying to find the flux because of one of these magnets, we can't just find it from a north or a south or a plus or a minus. We have to do it from both. What that means is the following. If I have some unit of magnetism, let's say this bar magnet here, it's going to create magnetic field lines, as we've seen numerous times now, that look like this. And if we try to find the flux through some surface that is, let's say, surrounding our magnetic charge or magnetic unit there, it'll look something like this. So let's just draw any shape around it, all right? Here we go. Just going to draw a shape. Doesn't have to be perfectly symmetric around it right now. There's a surface. There's a surface represented by that line. It's not a path. That's a full surface, like an egg, if you will. So basically you created a Gaussian surface, but it's not a Gaussian surface here. It's just a closed surface around that magnetic unit. Well, then what are we going to get for the magnetic flux through that surface? What's the magnetic flux going to be through that closed surface? Think about it. We've got magnetic field lines going out of the surface, and we have the same number of magnetic field lines coming into the surface. What I mean by that is, notice that here, that is here, 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 and here, I have magnetic field lines piercing the surface. That's flux. That's flux right there. I should be able to calculate how much flux I have based on the strength of the magnetic field, where the surface is, etc., except I don't have to, because notice those exact same lines are coming back in here, here, and here. So in fact, all those magnetic field lines that leave the surface also come back into the surface. And this is always going to happen. Anytime you have a closed surface around a magnetic charge, because that magnetic unit is going to have both a plus and a minus, all the field lines that leave are also going to come back in. And so you will always have a flux of, if I add up all of them coming out and all of them coming in, you're going to get zero. You're going to get zero for our magnetic flux. And so we can see that the magnetic flux through the dotted surface, and really any closed surface, is zero. Okay, so that is a very different result than what we got with the electric field. And if you recall, with the electric field and the electric flux, really quickly, I won't dwell on this. If you're interested again to find this out, I'll refer you to the lecture about Gauss's law. But typically with Gauss's law, we will have a positive or a negative charge within it. We can create a Gaussian surface around it. Doesn't really matter what the shape is, but usually we use a symmetric to make our left-hand side easier to solve for the electric field. But we're not solving for the left-hand side. We're just solving for the flux here. Well, the flux is dependent on these electric field lines that pierce the surface in all directions, like so, in 3 dimensions. And we can calculate the flux through that, and we've seen this before, is just Q enclosed divided by epsilon naught, like so. And so this is standard and eventually gives us Gauss's law, where we have E dot dA equals Q enclosed divided by epsilon naught. Again, notice the difference between that and what is happening here, where now all of our electric field line or magnetic field lines are coming out, that is going through the surface, but then the same number is coming in at the same strength and essentially the same distance away. And so you're going to get magnetic flux here of 0. And that's going to give us the following equation. I'll write it here. The integral of a closed surface. This is where the closed surface integral comes from. We treat it the same, but we're acknowledging that that surface is closed, of B dot dA is equal to 0. And that's essentially what we're going to conclude here with. I'll write it just one more time. Maybe I won't put a square over here. It's not two separate things, it's the same thing. And so let's just present it here at the bottom and make a couple of quick notes. Integral of B dot dA equals 0. So what is the magnetic flux through or around any charge? If you put a closed surface around any charge, you're going to get a magnetic flux of 0. This is the magnetic flux. And you might consider this Gauss's law for magnetism. Not to be confused with Ampere's law for magnetism, which showed similar techniques that we use for Gauss's law, but was a B dot ds, and it was not a Gauss's law at all. This is kind of, or quite appropriately, Gauss's law for magnetism. So now we get to move into inductance itself, and we're going to quantify this idea of inductance through something called Faraday's law. And this is going to be built upon a notion that we are familiar with. So when we were studying magnetism, we learned that if we have moving charges, that those charges create a magnetic field. And so whether we had a single charge, like a positive charge moving, we could use the Biot-Savart law of a charged particle to figure out what the magnetic field created by that particle is. We could also figure out the direction using our right-hand rule, etc. And we know that if we have a whole bunch of different charges, not just a single charge, that we can again create a magnetic field. And then that was given to us through both Ampere's law as well as the Biot-Savart law for a current carrying wire. So now I'm going to ask you to change your thinking a little bit. What if I asked you to consider the possibility that if I have a charged particle and it's moving, which is another way of saying current, if I have a current that creates a magnetic field, is it possible for the opposite to be true? Could a magnetic field move a charge? Could a magnetic field create a current? And so that's what we're pondering right now. We already know that moving charges, we needed that velocity, remember? Without it, we do not have the ability to create an electromagnet. We don't have the ability to take charges and have a magnetic field associated with them unless they are moving. And we've got a whole bunch of them where we have some current. And we know that that creates a magnetic field. We can calculate that value. We understand that value. But now I'm asking you, is the opposite true? And so let's set up a little experiment, something that no doubt has been done historically many, many times before. And what we're going to do is we're going to take a loop of wire, and we take that loop of wire and we connect it to an ammeter. We connect it to a device that reads the amount of current that's flowing through the wire. Now, we're not going to connect this to a battery. We're not going to connect it to a power source. We're not going to connect it to any kind of electric potential. And so therefore, it doesn't have a current. Right now, if I was to read the current through this wire, it would be 0. There's a bunch of electrons in here, millions and millions and millions of electrons, but they're not doing anything. But now what happens if I take a magnet? And so consider this Lego to be a magnet, where this side here is the north side and this side here is the south side. what's going to happen when I move my magnetic field towards and away from that wire. And consider again what would happen if I flip directions. South in, south out. What is going to happen, in fact, is that we will observe a current that is induced in our wire. We're going to start using this word induced. Induced means that it's essentially created through is a consequence of some activity. And here the activity is to change the magnetic field. When I take my magnet and I move it towards or away, what I'm doing is I'm altering the strength of the magnetic field. When I just have this wire sitting here by itself, there's no current detected. When I take a magnetic field and I put it very close to the wire, but I don't move the wire and I don't move the magnet itself, there is no current. There is no current. It's only the act of moving away or towards, basically changing the strength of the magnetic field in the wire itself, that is going to cause the current to be non-zero, to have the charges move. For us, what we're basically doing is we're creating a current through a changing magnetic field. And this is electromagnetic induction. So is the opposite true? Yes. And it is through the idea of electromagnetic induction. And so just to draw out this experiment that we're conducting, let's take a loop of wire like so. We're going to connect both ends of that wire to an ammeter. An ammeter is a passive device that is just reading the amount of current that is running through our object. It is not powering the current or anything like that. And so let's say we've got ourselves some kind of ammeter. It's a weird looking ammeter. Let me try that again. Let's say it's like a clock where we have 0 up here, but we're going to be able to move that value around like so. And so right now, if you look at that ammeter, it is detecting 0 current through our wire. Nothing is happening. We have electrons, but nothing else. Now we're going to grab a magnet, simple bar magnet. We'll direct one direction, let's say north towards and south away from, and we will know that the magnetic field that is created by our magnet goes in this direction, from north to south. You know that already. There we go. And so when I put that magnet down right there, and then I go look at my ammeter, I still see 0. I still see a 0. But what if I take the magnet and I move it towards the object with some velocity and away from our loop with some velocity, towards and away? What am I going to observe? I'm going to actually observe a change in the magnetic field. And depending on which way I go, I'll see the current go in one direction or the other direction. As I move the north side towards the loop, you'll see it deflect one way. That means that the current's running in one direction. When I move away, you see it going in the other direction. And so let's represent that. We'll put a velocity here, the velocity vector on our diagram. And let's say that the velocity is moving in that direction, and we see a deflection of the current, and we get a reading over here now. So it's non-zero. All right, so hopefully that gives us an idea as to how we can generate current through a changing magnetic field. Just a taste of it. We're going to definitely delve into this a lot more. Let's start by writing some of our observations down through this experiment. So what we're looking at is when we move the magnet into the loop, we detect current in the wire. If we stop, the current stops. And what we realize is that we can also take our magnet and we can invert it. We can put the south side towards our loop. Moving the south side towards the loop turns out to be the same thing as moving the north side away from the loop. Moving the north side towards the loop is the same thing as moving the south side away from the loop, as far as the direction of current goes, figuring out which way the current is going to go. So that's an observation. Moving an N-facing magnet into the loop is the same as moving either into the loop or towards the loop. Basically, all you're doing is changing the strength of the magnetic field in the wire. But if you go in the other direction, we see the opposite happen. So that way we're changing the we're changing the change in magnetic field. As you move a magnet towards the wire, the magnetic field is getting stronger and stronger and stronger and stronger. As you move it away, it's getting weaker and weaker and weaker and weaker. And so it's the change in magnetic field that is generating the current itself. Moving an N-facing magnet into the loop is the same as moving an S-facing magnet out of the loop. And vice versa. There is one other observation that we notice, and it has to do with how fast we move our magnet. If the magnet is moving quicker, then the magnetic field is changing faster. And what do you expect to happen to the current? It also increases. That's right. And so the velocity here is going to make a difference. So what do we have? We have that speed influences the magnitude of current. The faster we go, the stronger our current is going to be. Now, of course, if you have a limited range that you can go, if you're just going from here to here and you're going faster, yes, you'll have a stronger current, but for a shorter period of time. And so we're going to now have to define the current that is being generated through this process, and it's going to have a special name. We're going to call it the induced current. And we're also going to have a name for the voltage that is generated, the voltage that, here we're talking about the electric potential, the EMF, the change in electric potential that allows that current to flow. Because we know that a changing electric potential is what's required for a current to flow. So basically what you're doing by changing the magnetic field is you're creating an induced EMF, which we technically call a motional EMF. Emotional means moving, and so the fact that we're moving the magnetic field is going to create an induced current and an equivalent EMF. So the motional EMF induces a current and motional voltage. Using a changing magnetic field. All right, so we use some observations to figure out that, in fact, if I have a changing magnetic field, I can create an induced current and a motional voltage. I would like to know how strong they are. I would like to know how I create these voltages and currents and, figure out the equation to do it so that I can do a lot of it. Basically, what's happening here is I'm generating electricity. This is what we are starting to do. Up to this point, we've been relying on these chemical batteries to move our current around, but it seems that we can, in fact, induce a motional EMF and an induced current to essentially generate electricity. And that's all going to depend on Faraday's law. Now that we understand the concept of induced current and motional EMF, that is, somehow a changing magnetic field creates those things, now I want us to do is to introduce Faraday's law so that we can quantify those values and hopefully understand more deeply about induction itself. And so Faraday's law is built upon the notion that a changing magnetic field produces an induced current and a motional EMF. A motional EMF can be found from the following equation. This EMF is found through the derivative of the magnetic flux. And so that's why we had recently introduced the magnetic flux. We're going to need to understand it for this problem. But it's actually the derivative of that magnetic flux. That's it. The motional EMF is basically like the equivalent of a battery being attached to our circuit. So again, imagine we had a wire like this just sitting here, not attached to anything, and so the current is not going. There's no electric potential across the circuit. But if I was to create an electric potential by putting both sides onto a battery, then I have an EMF that's going to create a current. Now I'm saying there's a completely different way for us to do that exact thing. By having a magnetic field and changing that magnetic field near our wire, we are inducing a current. We're making the current flow, but that means there's also an electric potential difference that we can quantify, and that is called the motional EMF. And how strong is the motional EMF? the motional EMF is equal to the derivative of the electric flux. We know what that equation is, of course. We just finished with it. Let's write it like this. Now you might be saying to yourself, why aren't you giving me an equation for the current? Why are you just giving me the voltage? Well, you can go from voltage to current very easily through Ohm's law. And so if I give you one, you can do the other. Fairly straightforward. And so now let's put in our equation for the flux. We define flux as the integral of B dot dA with respect to t. All right, so this is how we're going to calculate our motional EMF, and this is Faraday's law. Interesting. So the derivative part of this equation makes perfect sense to me. It's totally consistent with what we learned when we had a changing magnetic field. If I, again, just take a magnet and I put it near a wire, I don't induce a current because even though I have a magnetic field, that magnetic field is not changing. The derivative is the change. d by dt is the same thing as essentially the change in the flux divided by the change in time. In fact, we will use versions of this equation where this is the change in the flux divided by the change in the time. And so you'll see that, but I'll leave it off for now. Okay, so what I want to do is to analyze this equation because we had already observed that a changing magnetic field induces a current, creates a motional EMF. And that's what that equation is saying. That equation is agreeing with that idea. If B is changing, I can take its derivative and get a number. And that number is going to help me find the motional EMF. But that equation's way more complicated. That's not dB by dt. If that was dB by dt, we'd be done. That would be it. It would be a changing magnetic field creates an induced current and motional EMF. But now I am seeing that in fact there is more to the equation. Is there other things that can perhaps change? Other things that can vary to create my motional EMF and induced current? Basically what I'm asking you to do right now, and maybe a good idea is to pause the video, is I want you to think about this equation, this B dot dA, and think about how it could physically change from one time to another time, allowing us to have this generation of electricity, this electricity generation caused by our change in flux. So remember, once again, motional EMF is related to the change in flux. I thought it was just the change in the magnetic field. That's what we discovered from our observation, but it's more than that. And so I want you to take a second and answer the following questions before watching me do them. What are the 3 ways to induce a current? And a motional EMF. If you're doing one, you're doing the other. From the above equation. I'll help you with the first one because we already observed it. The first thing is B. Obviously, if B, the magnetic field, is changing, then I have the ability to take the derivative of something that is not 0 and get a value. Now, if this whole thing is 0, if this whole thing ends up being 0, the derivative of 0 is just going to be the same as any constant. Basically, if it's a constant, forget if it's 0, if it's any constant, we're going to take the derivative and get 0. We have no motional EMF in that case. But if we have things changing, for example, B, then we will generate electricity. Pause the video at this time and find me 2 other things that can change to create our induced current and motional EMF. Do that now. Okay, so I think the second one you probably were able to get. The third one was a bit tougher. The second one is area. Yeah, exactly. If this dA, which will eventually turn into an A when we take its integral, is going to produce a changing area, well then that also should generate electricity, A. And the way we do that is to change the size of the circuit, or wire, etc., exposed to the magnetic field. So, for example, if your magnetic field is constant, maybe it's produced by some device creating a constant magnetic field, turns out that you can actually change the area. You can change the area that is exposed to that magnetic field, and it will also generate a current. So let's look at an example of trying to change the size of the circuit exposed to the magnetic field. Imagine a scenario where you had a magnetic field that was, let's say, going into the page, or let's say this is a tabletop. That'd be even more interesting. So I'm generating this magnetic field. We are looking down at a tabletop. So looking down at the tabletop, and we're going to have a wire like so. That wire is going to be moved back and forth along the surface of our tabletop, or above it, it doesn't really matter. But basically, more and less of it are going to be exposed. And so we're going to move it this way, that is this way, and we're going to move it that way. And what that does is it changes the area that is exposed to the magnetic field. Right now, the area that's exposed to the magnetic field of this wire is this area here. That's the amount of area that is on the magnetic field. As we move it, then we can have more or less of that area exposed to the magnetic field, which is going to induce our current. And so this is A, like so. And so we can take that and use that as our second magnetic field, magnetic flux, and changing that is going to induce our current. Okay, the third one. Did anyone get the third way that we can change the magnetic flux so that we're inducing the current? Well, look at that equation. I'm like, well, there's only 2 things in that equation. There's only B and there's only A, right? Wrong. What's the third thing? Theta, the angle between the 2 of them. And so our third one is theta, and it's dependent on the fact that B dot dA, even neglecting the integral for 1 second, of those 2 vectors is going to be B dA cos of theta. So in fact, if B is constant, if dA is constant, but theta is not constant, then you are inducing a current. You are creating a motional EMF. You are generating electricity. So all you have to do is change the angle between B and A. All right. Well, that doesn't seem so hard, right? So once again, if I have my loop of wire like so, and let's say I've got a constant magnetic field that's generated by this magnet here. And so my magnetic field is constant here. My area that's exposed to my magnetic field is also constant. But what if I change the angle? What if I change the angle constantly? What if I'm rotating this around in the magnetic field? Well, theta keeps changing as I do this. As I rotate this around, my theta continues to change. B stays the same, A stays the same. And so what is actually happening is that we are generating current, that we're creating an induced current, we're generating electricity, we're producing a motional EMF. Now it's just the angle between the two. The wire doesn't have to be the one that changes, of course. The magnetic field could change as well, right? If this was static and for some reason our magnetic field rotated around, then you would get the same outcome. And so this seemed more obscure to figure out, but this is actually how you generate electricity. This is the method used in modern power plants, other than solar energy farms. Basically every other one. We'll talk about this in more detail. For the most part, we are changing the angle between our magnetic field and our wire to generate electricity. So change the angle between B and A. And so the rate of change of these things, how fast they change, is what's going to decide the strength of our motional EMF. And so we have, once again, our motional EMF here is equal to the derivative of the magnetic flux with respect to time. And so if it's a bigger change in a shorter period of time, whether it's B, A, or theta, you will generate more electricity. Now, this is going to be a pretty traditional way for us to calculate motional EMF and then use Ohm's law if we have to calculate the induced current. But there's something very interesting that we can also do to this equation to not just make it more complex, but to create an understanding between two seemingly different ideas that we have had in this class so far. See if you can follow me. Track what is happening with this EMF. Remember that the EMF is just an electric potential. It's an electric potential difference, technically. And we had called that V. We know that the electric potential is related to the electric field. Don't recall that equation. It's been a long time. We basically used it the first time we introduced electric potential, and it was that V was equal to the integral of E dot ds. We never solved that equation. We never solved that equation when we first introduced it, but it helped us to kind of understand the relationship between the two of them. What I'm going to do is I'm going to set my EMF to my electric potential. What that allows me to do is to set the electric field dot product with my ds vector equal to my derivative of flux with respect to time. Now, I've been throwing absolute value signs on this so far because we weren't worried about direction. We'll get to direction at another time. But technically speaking, this is actually equal to the negative. Our magnitude was hiding that negative sign. And so now we have this relationship. We have the relationship between electric field and magnetic flux. That seems weird. We have yet to have any kind of link between electrical charges, etc., and magnetism. But it seems like this motional EMF, this electric potential, might be that link. And that link can become even clearer if we substitute out our equation for the electric flux. Let's write this down. And I think it's safe to say that this is the most complicated looking equation that you encounter in first year university. The left-hand side is E dot ds, that is the electric field dot product with our ds vector, minus the derivative of the integral of b dot dA with respect to time. That, I admit, is a very, very challenging looking problem. We've got an integral on one side and a derivative of an integral on the other side. But if that's what you're focused on, if that's what you're looking at and saying, hey, this is going to be difficult for me to solve, you're looking at the wrong thing. Because what we have done is we have created an equation that has the electric field and the magnetic field in the same equation. That is a surprising result. That is an important result. That is a fundamental truth in physics that we've stumbled upon, that in fact the electric field and the magnetic field are related to each other. In many ways, you can consider them two sides of a more important, vast idea of not electricity, not just magnetism, but electromagnetism. Electromagnetism is a fundamental concept that we will define a little bit more in depth later, but you'll certainly appreciate it much more in later years. What this is saying on a more practical level, if you don't want to get all philosophical about the electric field and magnetic field being in the same equation, you can think of this as saying that a changing magnetic flux and I mean, that could be a changing magnetic field, so I'll put it like that because it does have a bit more impact to say, creates an electric field. That's what's happening here. Wow. Wow. When I look at that left-hand side and I look at that right-hand side, what it's basically saying is, look, on the right-hand side, if I have a changing electric flux, and one of the possibilities of creating a changing electric flux is to change the electric field. So if I have a changing electric field, I'm going to make, whoa, I got that wrong. Look at the right-hand side once again. It's saying that if I have a changing magnetic flux, and one way I could have a changing magnetic flux is to have a changing magnetic field, that's going to actually produce the electric field. A changing magnetic field creates an electric field. Fascinating. Please note that this is true for a single wire. If you had a whole bunch of loops, this is true for a single loop. What if you have a whole bunch of loops? What do you call a whole bunch of loops that we've purposely put together? That's right, a solenoid. So let's just add, what would this equation look like for a solenoid? And we won't even do this equation. but our most simplest one. So all we're writing is that for a solenoid, we have the motional EMF is equal to the number of loops, n, multiplied by the same thing. That is the changing magnetic flux with respect to time, or the derivative of the flux with respect to time. And all we have for n here is that it is the number of loops. Let's do our very first example of a Faraday's Law question. Consider this. A magnetic field that decreases uniformly. Okay, so we have a changing magnetic field in this problem. It is changing uniformly. It's very, very helpful in figuring out how to deal with this, as I'll show you in a second. From 1.0 to 0.40 Teslas in 1.2 seconds. We're going to take a 6 centimeter loop wire, and that is the diameter. With a resistance. We're giving the resistance because I'm eventually going to ask you for the induced current and this is just the resistance of the wire itself, so it's very tiny, 0.010 ohms. And I'll give you the angle as well, which is going to be necessary. The wire is perpendicular. Run out of space. To the magnetic field. And your question is, what is the induced current in the loop? All right, there we go. I want you to consider a magnetic field. The magnetic field is decreasing uniformly from 1.0 Teslas to 0.40 Teslas in 1.2 seconds. A 6 centimeter diameter loop of wire with a resistance of 0.010 ohms, which is perpendicular to the field. That's not really a sentence, is it? A 6.0 diameter loop of wire with a resistance of 0.10 ohms and is perpendicular to the field. Let's say is placed in the magnetic field. Let's try this. Say there is a, that's a sentence, there is a. All right, so let's make a list of what we actually have in this problem. We've got to think about how the magnetic field changes with respect to time here. And so the change in the magnetic field, delta B, is just going to be equal to what it was initially, minus what it ends up being, giving us 0.60 Tesla. Our change in time, while that's happening, is 1.2 seconds. And then I also have my radius of my loop, 0.03 meters, and we've got our resistance of the wire, 0.01 ohms. Okay, so that's all we've got to try to figure out the induced current. So I start by writing down my most general form of Faraday's law, and that is that the motional EMF is equal to the derivative of our magnetic flux with respect to time. All right. So it's like that. But because we are dealing with a uniform magnetic field that changes uniformly with respect to time, we can write this instead of as the derivative, as the change in. This is the change in flux divided by the change in time. And what the change in flux is equal to, well, let's figure out what flux is equal to first. In general, we have flux equal to B dot dA. This is not an equation that we've dealt with very much at all, and so let's be careful with it. But we start, as usual, with our dot product, B dA cos of theta, where theta is going to be the angle between B and dA. What is that angle? What is that angle? Well, I remember it saying that the wire was perpendicular to the magnetic field, which makes me want to put 90 degrees, but that would be incorrect. Because if you recall, I'll draw you a little picture here. If I have a magnetic field in this direction, and I put a loop of wire perpendicular in it, it's going to look like that. And basically, I'm kind of drawing it at an angle, but basically we have the magnetic field lines going this way, and our loop is perpendicular to the magnetic field lines. And so you're saying to yourself, well clearly it's 90 degrees. No, because remember, this is the area that we're talking about of this wire. This is going to be A. But right now we're just looking at dA, where dA is going to be a tiny bit of that, and it's going to be perpendicular to the wire itself, to the surface of the loop. That's the best way to put it. So this is the surface area, not of the wire, but of the loop. Let's say the surface area of the loop. And so, what is the angle between B and dA, actually? That's right, it's 0. And so this becomes the integral of B dA cos of 0. And it's all too familiar. You have done this many, many times. Now the B slips out. The integral of dA is going to be A. And so you end up with B times A. And you've done that so many times before. Every time we've done dot product with an integral, we've had something similar to happen. We've done this with Gauss's law, and we ended up with E times A. We've done it with Ampere's law, and we ended up with B times S. And now we're doing it with our magnetic flux, and we're ending up with B times A. We're used to doing this now. It is common for us, but we want to understand where these things are coming from. Okay, well, A is not changing. The area of that loop that's exposed to the magnetic field doesn't change. And so we can write that the change in the magnetic flux is actually the change only in B multiplied by A, multiplied by A. Hopefully that makes sense. Because A doesn't change, we don't deal with the change in it. And so, might as well calculate this as a number. While we're here, we know the change is 0.6, and our area of the wire, the radius was 0.03. It is a circle, so the area is pi r squared. Like so. In case you don't see, that's delta B times pi r squared. Good stuff. And just out of curiosity, since we haven't actually calculated a flux before, let's see what this would look like. You would get 0 point, and go ahead and do this before me. Pause the video if you need to. 0.169 Webers. That's not the answer that we're looking for here, but it's a nice little segue into finding the motional EMF, because the motional EMF, as we saw, was the change in the flux divided by the change in the time. So just take that value and we divide it by our time of 1.2 seconds to give us our voltage. Our EMF, our motional EMF, is the tiny little value of 0.01357 volts. Well, that's a little bit disappointing. We are generating quite a small amount of voltage through this wire, despite a fairly large change in the magnetic field. And so let's finish the problem off, because we are looking for the induced current, and we'll find it from Ohm's law. So V equals IR, or the induced current equals our motional EMF. So anytime you want to go from motional EMF to induced current, we're just using the motional EMF divided by the resistance in our wire. And that is 0.001357, all divided by 0.01. That's volts, that's ohms, meaning my final value will be in amps. And we have an induced current with 2 sig figs of 0.14 amps. That's it. And so mathematically a very simple problem to do, but physics-wise fairly difficult to understand what all of the different terms were and how they related to each other. So we will definitely get more practice with Faraday's law very soon. Now that we have an understanding of inductance, the idea that if I have a changing magnetic flux through a circuit, I'm going to create an induced current, a motional EMF. I'm basically generating electricity. I wonder where else this idea of inductance can be used. What about in a circuit itself? What if I have some circuit, let's say a simple circuit attached to a battery, and I know that the current in that circuit is creating a magnetic field. We know that all current carrying wire creates a magnetic field. If that magnetic field is stable, steady, because the current is stable and steady, then I have nothing to worry about because I don't have a changing flux. But what happens when the current changes? Well, the magnetic field changes as well. Well, if I have a changing magnetic field, I have a changing magnetic flux. And if I have a changing magnetic flux, then I'm going to have the possibility of inducing a current, of creating a motional EMF, even if the circuit already has a regular battery in it. And so this is the concept of self-inductance. It turns out that circuits can actually induce currents inside themselves. They don't need an external battery to do this because they themselves are, or they don't need an external magnetic field to do this because they themselves are creating magnetic fields. And if that magnetic field is changing, well then you should be inducing current. It is originally going to look like a problem. It's going to look like something that is detrimental to our circuit, to have this induced current or motional EMF suddenly appear where you don't want it to. But very quickly it's going to lead to the method that creates our next type of circuit element. We're very, very close to jumping back into circuits, and we're going to introduce a brand new circuit element that is going to be reliant on this concept of self-inductance. So let's learn what self-inductance is first, so then we can get to the inductor. So let's start with a very simple circuit. We'll put a switch right here. We'll put a resistor and a battery. So this is a loop of wire, but it's not the simple loop of wire that we did when we learned about the idea of inductance. that was just a loop of wire that had a natural resistance to it and no battery at all. Now we have a battery, and that battery's job is to create an electric potential and to create to make the electrons move, to have a current. Right now, nothing is happening in this circuit. In this circuit, the switch is open, and so there is no place for the current to go. But what's going to happen when we close the circuit? What's going to happen when we close the switch? Well, you know what happens. We've dealt with these type of circuits before. You're going to start to increase your current, right? It doesn't go all the way from 0, as it is now, to its maximum value instantaneously. It takes a while. It takes a little bit of time to reach that value. So the current goes from 0 to I over some period of time. A short period of time, but a period of time. All right, well, once the current starts to flow, I know it's going to go in this direction, like so. Oh, we forgot to close the switch first. Let's do that before we try any of that. And so, click. That is a closed switch and a closed circuit. Why? There we go. That's fine. And now my current begins to flow. It flows in this direction, starting at 0 and increasing. What I'd like you to think about is, what is the magnetic field produced by this circuit? What is the magnetic field produced by the wire in the circuit? Well, we can use our right-hand rule to figure out the direction of it, and use Ampere's law, for example, to figure out the magnitude. Let's look at that wire segment for a second. I'll use my right-hand rule. So my thumb is in this direction. So this is Ampere's right-hand rule. And my curly fingers are the direction of the magnetic field. So it's going like this. It's going like this. And I can represent that on my drawing the following way. There we go. And so that's the magnetic field. I mean, it's everywhere through all of the wires, but that's the one that I've drawn. And as we're increasing our current from 0 to I, what's happening to that magnetic field? Well, the higher the current, the stronger the magnetic field is going to be. So originally when the circuit was open, it also was 0. The magnetic field itself was 0, but as we close the circuit, the current gets higher and higher and higher and higher. Magnetic field gets higher and higher and higher and higher. What we basically have here is a changing magnetic field. During the time it takes for the current to reach its maximum value, it is going to have a changing magnetic field. But a changing magnetic field also produces a changing magnetic flux. And a changing magnetic flux creates a motional EMF and an induced current. Well, that's weird. That's super weird, because in this problem, I already have a current. I already have an EMF, but now I'm inducing another one. And out of curiosity, what do you think the direction of the current and the motional EMF are? Do you think that this self-inductance is going to help the current? That is it going to strengthen the current in the direction it's going? Do you think that the motional EMF is going to enhance the EMF that is already there and also work in the same direction? When has that ever happened in nature? When have we ever naturally encountered a physical concept that has helped us to do something? Concepts like friction tend to be more common than not, where there's this idea of opposition to what we're doing. That's exactly what happens here. We are going to create a motional EMF and an induced current. They're going to work against our circuit. They're going to slow down the progress of where our circuit wants to get. Let's write that during this time, over a period of time, during this time, the current produces a changing magnetic field and so what that means is if the magnetic field is changing, the flux is changing, and the derivative of that flux cannot be zero. Because the magnetic field is not a constant, the magnetic flux is not a constant. The derivative of that not constant is not zero. It's an unnecessarily big zero. There we go. And so what are we actually doing? We are creating a motional EMF. So remember, this motional EMF is equal to, and we've always kept the absolute value signs there, because we were only worried about the magnitude of that value. But now I'm going to keep the negative there to show us that we are creating a motional EMF and induced current in the opposite direction of I. That's what that negative is telling me. It's the opposite direction of the current. That is the natural current produced by the battery, and the battery's EMF. It's basically like this fake battery that is in the opposite direction. And so if you have a plus minus on this side, it's going to be plus minus in the opposite way, counteracting the effects of that battery. And so what is the result of this? What is the consequences of having a self-induced current and EMF? Well, what you're basically doing is when you close that circuit, you want it to go from 0 to I, and this idea here is going to create a current in the opposite direction. It's a small current, but that current is going to be fighting the current that is trying to get up to its maximum value. Basically, what you're doing is you are reducing the quickness of getting to a continuous constant circuit. So let's write it this way. All of this results in a gradual increase of current until it reaches its steady state. Once it hits its steady state, once it hits its maximum value of current, then our magnetic field becomes a constant. And a constant magnetic field means a constant magnetic flux, which again means no motional EMF, no induced current. But until you get there, until you get to that value, we will have this slowdown of that increase, this fighting against the change. Basically, the self-inductance wants to keep things the same. If you're wondering which way self-inductance works, it's always trying to keep things the same. It doesn't like change. You know how some people are like that. They don't want it to change. They want to keep things the same. That's what self-inductance does. And we can quantify that value with the following. We can say that the EMF created by this self-inductance can be quantified in the following way. Where L here is our first inductance quantity, inductance. And that's going to quantify our value. Let's try to understand this equation a little bit better. Let's maybe compare it for a second to V equals Ri. That's essentially the resistor equivalent of our equation there. So V equals Ri, where V is like the motional or EMF, I is I. And so L takes the place of R, but instead of having I, we have di by dt. Let's define L a little bit. The inductance of a circuit or of an inductor. So just as a circuit naturally has a resistance, a circuit naturally has an inductance as well. But if you want to manipulate the resistance of the circuit, you create a resistor where the resistance is so much greater than the rest of the circuit that it manipulates what is happening in the circuit. We can create an inductor as well. An inductor is going to purposely use the physics of self-inductance to manipulate the circuit in a way that we want. So the inductance of a circuit or inductor is dependent on the geometry of the wire. And by geometry, I mean things like the number of turns of a wire, in case you have multiple loops of your wire. That's very important. The radius of the loop, etc. Just as a resistor was dependent on what it's made out of, but also the other characteristics, geometrical characteristics. And so this new term inductance is going to be given in SI units by, if we look at this value, it looks like it's voltage divided by current time, or V times seconds divided by amps. And that looks like not the most convenient set of units, and so we call it henries. That's right, henries. How many henries do you have? Now, we can also find the inductance of a solenoid, and the reason we'd want to do that, again, is because as we've learned, solenoids have a lot of different turns, and if we have hundreds, thousands of turns, that's obviously going to increase our inductance. So much so that a solenoid is actually an inductor, a device that you're purposely making and using to induce a current or motional EMF is called an inductor, and it's solenoids that are used here. And so we want to figure out what the inductance of such an object is. And so we'll write let's use a capital here, for an for a solenoid or inductor, now we're starting to equate them as the same thing, we are going to have two equations that give us the EMF for the due to the inductance. We had our motional EMF for a solenoid equal to minus n derivative of the flux with respect to time. All right, so that's our standard equation for the motional EMF due to a solenoid. Now, in general, for an inductor, we have that this is also equal to minus L di by dt, the derivative of the current with respect to time. We just figured that out right up there. And so now we're putting both of those together to see if we can figure out the inductance of the solenoid. And so if we solve for this L over here, the negative signs cancel. We move the I to the other side, and we can simplify things to the inductance is equal to N times the flux, all divided by current. That's it. Nice and easy, right? So we've got our N for the number of loops in the solenoid. We've got our magnetic flux, and we're dividing by the current. And this is our inductance of a solenoid. As we've said, inductors and solenoids are the same thing, but what we're talking about now as inductors is that they are circuit devices, like resistors, like capacitors. We're now going to purposely put inductors into our circuit so that we can manipulate them. And we can write that inductors are solenoids and have a much bigger inductance, than the rest of the circuit itself. So in fact, we can ignore the self-inductance of the circuit. We just, a few minutes ago, finished learning how a circuit can self-induce a current. But now what I'm saying is, look, if you put an inductor into that circuit, it's going to have an inductance that's far, far greater than any natural inductance that comes from the loop of wire that's going through it, such that we can ignore the natural inductance or self-inductance of that circuit. Just as if we can ignore the resistance in a wire if we have a resistor in our circuit, because those resistors and inductors are going to be so much bigger than the rest of the circuit. So circuit elements called inductors do the following. Let's think about it. What would an inductor do? Well, self-inductance of a circuit without an inductor, without a solenoid, was trying to slow down the change, in the current. As we switch from 0 to I, and the same thing would have happened if we switched from I to 0, there is a very quick fall off or increase to our final value, but the self-inductance slows that down. And so what we're doing when we have an inductor is that we have a circuit element that will slow down the rate of change of current. So much so that we can manipulate it. We can use different inductors with different inductance to control the rate of change of current. That's very different than anything a resistor does, for example, right? The resistor has no dependence on the rate of change. All it does is affect the relationship between voltage and current at any given time. But what we're looking at here is a way to manipulate the change in current. And so when we put these into circuits, they look like the following. They look like little coils of wire. Try that one more time. There we go. And again, like so. And so each of these represents a single inductor, and it will have a property of inductance given by the capital L. And so because these inductances are inducti, are going to be so high, so dominant, that if a circuit has an inductor, or more inductors, but basically has any inductors, at least one we should say, maybe that's the best way to put it, has at least one inductor, the rest of the circuit has a self-inductance that can be treated as 0. So basically we can ignore any self-inductance in the circuit. Now, the only other thing we need to know about this current that we're inducing is its direction. And we haven't talked about this, but you need to understand which way the current is being created in the circuit. Which way is it being induced? Whether you have a circuit that's already attached to a battery or one that is not, we use Lenz's law. And Lenz's law says the following. It says that the induced current flows in the direction that will produce a magnetic field to balance or counteract. Basically, balance is the wrong word. I don't like that. Let's get rid of that, because it's never going to be able to balance the original. So let's say that will produce a magnetic field to counteract the original change in the magnetic field. So Lenz's law states that the induced current flows in the direction that will produce a magnetic field to counteract the original change in the magnetic field. Now this is a bit confusing to think about and a little bit, I think subtle is the right word. Let's see if we can do a Lenz's law, which allows us to figure out which way the current would flow in this wire if I was to say move the magnetic field through it. And so once again, the red side here is going to be the north or the positive, and so the electric field is coming out this way and going around. And so if I was to move this upwards, then it's as if the magnetic field in this direction is increasing. So if the magnetic field in this direction is increasing, what's going to happen as far as the induction goes is you want to counteract that change in the magnetic field or the change in the magnetic flux if it was being done a different way. And so if it's increasing this way, we want to create sort of an induced magnetic field in that direction. And so now we know the magnetic field that is going to be created by the induced current. It's the induced current that's going to create this induced magnetic field, but the direction of the induced magnetic field has to be opposite the direction of the increasing magnetic field. And so, for example, once again, it's going in this direction and it's getting higher, so our induced magnetic field is this direction. And now to figure out what direction it's going in, the current, all we're going to use is our Ampere's right-hand rule. And so we know which way the magnetic field is induced. It's inwards. It's down like this, and we just see which way our thumb is pointing. And our thumb, no matter where you do it along this wire, is going to create a current going in that direction. It's a bit difficult to see, I admit, sort of here in the video, so why don't we try a quick example of Lenz's law, where we're going to take our loop of wire and we're going to, let's have a direction for the magnetic field. So this is the magnetic field that already exists here. We'll call that the magnetic field B, and let's have an increasing magnetic field. So that's the direction of the magnetic field, but if it was just a stable old magnetic field, there would be no flux and therefore no induced current. Now, if this is increasing, maybe steadily increasing, for example, then we're going to induce a current. And we're going to induce a current such that it's going to produce an induced magnetic field that counteracts that magnetic field. And so you might consider this the induced magnetic field. Like so. And now we just use our right-hand rule on the induced magnetic field to figure out which way the current is going. And so the magnetic field inside the wire is going down. It doesn't matter where you grab that wire. All around it, you'll see that your curly fingers need to be pointed down within that wire, and my thumb gives me the direction of the current. The thumb is pointing in this direction, like so, like so. If I was back there, it would be going that way. And that gives me the direction of the induced current. Okay, let's try something a teeny bit different just for practice. And once again, we'll create this loop. And this time, let's have a decreasing magnetic field downwards. So we already have our magnetic field, here it is, running through our wire, but it's going to be decreasing. So it's getting smaller and the direction is downward. What that's going to mean is that our magnetic field that's going to counter that change. It's the change that we care about that induces the current, not the magnetic field itself, is we're going to, once again actually, create an induced magnetic field downwards. Since it's getting smaller, the downwards one is getting smaller, this magnetic field is counteracting that decrease. And once again, fingers downwards as we go into our loop. I suppose it's sort of behind me here. I'll go on this side. And I can see clearly that my thumb is pointing around in that direction. And so we can draw it like so. That's our induced current. That's completely consistent with what I thought would happen. The direction of the magnetic field and whether it's increasing or decreasing is what's going to determine the direction of our current. Now, we know that these situations for self-inductance mainly only seem to occur when we have a switch, when we're going from 0 to some Imax, or when we open our circuit, we're going from some Imax down to 0. And those are very specific circumstances for our DC circuit. Apparently, inductors have no role to play in a circuit when there is a steady current, seemingly. So let's deal with not a steady current. Let's deal with an alternating current.